We are going to be discussing section 3.3 in your textbook, and the topic of section 3.3 is a type of a force system called a couple. Now, a couple is a very specific arrangement. In order for forces to be in a couple, they have to be exactly opposite in direction or opposite in sense and equal in magnitude. So in other words, it's two forces of the same magnitude pointing in the opposite direction, separated by some distance. Now, the physical importance of a couple is, if you think about it, if you have an object being acted upon by a couple, the summation of forces in the vector directions due to the couple are equal to 0, and yet there is a tendency to a rotation. So a couple will have that tendency to produce a rotation without moving it in a linear manner or in a translation. So the moment of a couple turns out, if you remember, moments in general are r cross f, and if you go through the math on that, you see that the magnitude of the moment of a couple is equal to the distance separating the two, or the vector separating the two, times the magnitude of the force times the sine of the angle between r and f. And the direction is either going to be negative or positive if we're discussing this in 2 dimensions, based on whether that rotation is clockwise or counterclockwise. So with the force couple system shown here, you can see that if we had a point anywhere on a body that these two were acting upon, that the rotation would tend to be counterclockwise, so the sign for this couple would be positive. Since it's a rotation, the moment of the couple is going to be perpendicular to the surface of, or to the plane in which f and negative f are acting. So it's going to be, if f and f are in, if f and negative f, or f and f prime are in the horizontal plane, m will be vertical. It's also said that it's a free vector because it's really not going to matter where you consider it as long as the body is rigid. So you can think about the moment being here, or you can think about it being here or here. Anywhere on that rigid body, it's going to have the same effect. So two couples, that was interesting. Two couples have equal moments if f times d is equal to f times d, and if the two couples lie in parallel planes, and if they have the same sense or tendency to rotate. So once again, in 2 dimensions, if f and d are in a plane, or f and f prime, f and f minus are in a plane, then m is going to be perpendicular to that. To add couples, you can add the moments of the couples. And so in other words, you can use Vernon's theorem, and you can just take r, which would be the distance, times the magnitude of the two forces. And when I say add the magnitude, that's a vector addition, and when I say multiply, that's a vector multiplication. So we're talking about a cross product. The sum of two couples is also a couple that is equal to the vector sum of the two couples. So the big deal here is the magnitude of the moment of the couple in order to produce that equivalency. Couples can be represented by vectors, and so basically what we're saying is that couple vectors obey all the law of the addition of vectors. Couple vectors are free vectors, just like the moment of a couple, and they may be resolved into components. So if you have some moment of a couple, m, you can resolve it into the piece of m that's in the x direction, in the y direction, and the z direction. Although, as we were saying earlier, if f is, for example, in the xy plane, the moment is going to be, the moment of that couple is going to be purely in the z direction. All right, so here are some other ideas about couples and the resolution of a force into a couple and to a force. Sometimes if you have a force, say the magnitude of this force is 6 units, as long as you maintain, you can add other forces that can be a couple and a force if you want to move that force. In other words, if this is 6 units, an equivalent system will have a magnitude of 6 units, and you can resolve the rest of it into a couple. Now, the reason for that is that you can't simply move a force because the moment is going to be different. In other words, if we look here at the first diagram, if we have a force applied here at point A, but we really want a force applied at point O, if we just move it, we'll have the same summation of forces, but the moment will be different about every point. So what we really do then, in order to move it to a force, is we create a couple that is F and F minus, which once then that becomes a free vector. Then we can move F to the point that we choose, and based on that relationship R cross F, we can develop what that moment looks like. Then the moment becomes a free vector, and the additional force is not a free force. It has to be applied at O, and the effect of this force and this moment is exactly the same as this force alone. So the 3 forces may be replaced by an equivalent force vector going different, and that's referred to as a force couple system. So once again, couple always means that exact same thing. 2 forces equal in magnitude, opposite in direction. All right, this slide talks a little bit about the resolution of a force into a force at O in a couple. So this is sort of the opposite of what happened in the previous slide. So revolution of a force into a force at O in a couple. So we're just talking about how we would do that. This is more of a 3-dimensional treatment. And here is a problem of application. So sample problem 3.6 says, determine the components of the single couple equivalent to the couples shown. All right, so in other words, if you look here, we have 2 forces that are 30 pounds in magnitude. They are equal in magnitude and opposite in direction. We also have another couple, which is 20 pounds, once again, equal in magnitude, opposite in direction. And instead of writing this as 2 couples, we want to write it as a single couple. So in other words, 1 force and its negative equal and opposite in direction. All right, so the first thing we do here is we find the moments, the moment in the x direction, the y direction, and the z direction, based on the magnitude and the perpendicular distance between them, or the distance times the sine of the angle, whichever works. So the 20-pound force is in the x direction, so we have a y direction and a z direction for that moment, and the 30-pound force is just going to have a moment in the x direction. We have those 3 moments. Then we can say that if we have an equivalent force couple, so in other words, this is negative 540, the units would be inch pounds, negative 542 plus 240 and plus 180. Hold on a second. So there we go. Then if we find a force system that has that same moment of the couple, if we find a single moment that has a single couple that has that moment, it will be equivalent. All right. So there are only 2 more slides that we're going to talk about a little bit here. First of all is the system of forces reduction to a force and a couple. Any system of forces acting on any rigid body can be reduced to a single couple and a single force. The force is going to have to be applied at a given point, and then the moment of the couple will be a free vector. All right, and if the resultant force and the couple at O are mutually perpendicular, they can be replaced by a single force. But if the resultant force couple system for a system of forces will be mutually perpendicular if the forces are concurrent, the forces are coplanar, or the forces are parallel. So those are the conditions that need to be met. All right, so what we're going to do then is this covers the material in section 3.3. If you take a look at our Moodle page, that that lecture will be put right here, so there will be a link to lecture 13 covering section 3.3. And then I'll put a couple more homework problems here for you. Right now we should have 2. The first problem set is from 3.1. 3.1. The second problem set is from 3.2. So I'll put a couple of problems here from 3.3. Then we will cover 3.4, which is the last section in this chapter. And then we will have a problem-solving session. So our 15th lecture will just be a problem-solving section covering sections 3.3 and 3.4. All right, everybody, have a great day, and we'll see you next time for section 3.